A glass U-shaped tube of diameter 0.85 centimeters is used to determine the density of an oil. So as you can see in this figure, on the right side we have water reaching a height of 24.5 centimeters. On the left side there's oil reaching a height of 27.2 centimeters. And both of those liquids are in the column so that the two interfaces with mercury are at the same height. And you're given that the density of water is 1 times 10 to the third, or 1,000 kilograms per meter cubed. So in part A, you want to calculate the density of the oil. The best way to do this is to use one of the facts we know about fluids, and that is that at equal heights in a uniform fluid, the pressure is the same. So if we look at the mercury, at this height where the interface is, and at this height where that interface is, those two pressures have to be the same. So I'm going to start by saying that the pressure at point A is equal to the pressure at point B. Well, the pressure at point A is equal to the surface pressure up here, which is atmospheric pressure, plus the pressure from all this oil. So I can write PA as equal to PO, the atmospheric pressure, plus rho g h. And I'll put subscripts on here to represent that we're looking at the oil on side A. So it's the density on side A times gravity times the height on side A. That's equal to the pressure at point B, which is equal to the surface pressure or atmospheric pressure up here, plus the pressure from the water. So that would be PO plus rho gh again, but this time we'll put B subscripts on the density and the height. And now you can see that with this equation, you can subtract the PO from both sides, the atmospheric pressure, or the pressure at the surface. So you're just left with rho AGHA equals rho BGHB. So with that equation, if you divide both sides by G, that will also cancel out, and you're left with simply rho A HA equals rho B HB. We know three of the things in this equation. We're trying to find the density of the oil, which is rho A, but we know the height on side A, we know the height on side B, and we know the density of the water on side B. So just take this equation and divide both sides by HA. So those cancel out. And then we can just plug in the numbers. The density on side B, which is water, is 1 times 10 to the third, or 1,000, times the height on side B, which is 24.5 centimeters. You can leave it in centimeters if you want to, since you have centimeters in the numerator and denominator, or you can convert both sides into meters. Doesn't matter, you get the same answer either way. So 0.245 meters divided by the height on side A, which is 0.272 meters. And when you plug all that in, you'll get an answer of 901 kilograms per meter cubed. For part B, calculate the absolute pressure at point B, which is the interface between the water and the mercury. The absolute pressure is the equation we just used in part A. So the absolute pressure at point B is equal to PO plus rho B G HB. Just plug all those numbers in. We can say that the surface pressure is atmospheric pressure, which is 1 times 10 to the fifth, plus the density of B, which is water, that's 1 times 10 to the third, times 9.8 for the acceleration of gravity, times the height. This time the height does have to be expressed in meters, since we want the final answer expressed in standard units, so we have to use 0.245, and from that you get roughly 1.02 times 10 to the fifth pascals. So now we introduce a new tube, which is identical to the tube in parts A and B, except for on the left side of the tube you have this cone-shaped portion. And then you have the same amount of mercury in the bottom of the tube, so it's exactly the same as this one, and you pour the same amount of water and oil on both sides of the tube. So with all of that done, for part C, you want to indicate whether the new position of B relative to A is higher or lower, or if it's still at the same height. So if you think about what happens with this, when you pour the water on the left side, on the right side of the tube, because that side hasn't changed, the water goes up to the exact same height as before. The oil on the left side of the tube, because the tube is more open, the height of the oil does not go quite as high. So we can say this green represents the oil. Because the height on this side is now lower than it was up here, there's going to be less pressure at this interface, because remember, height depends on pressure. So because there's less pressure at this interface, that means the water still exerts more pressure, so this side over here will go down, so side B goes down, and then side A goes up. So the new position of B relative to A, you can check the blank that says that the new position of B is below A. For your justification, you can say that for the oil, the height becomes lower and that leads to lower pressure on, I guess we'll call it side A, which is the side where interface A is. So since there's lower pressure, that means that side A goes up and B goes down. And for part D, suppose you have a small piece of wood with density less than that of the oil, and it's placed so that it floats on the left side of the tube. So I'm going to get a small piece of wood, which I'll put in red, on this side of the tube, and it's put in there so it's kind of floating. Let's say it's just half submerged. First thing is, what does that do to the level of the oil? Well, since it is displacing it's displacing the oil, that means the oil has to go up. So if the oil is going up, that means it's higher, which is going to lead to greater pressure on the bottom. So the answer to part D is that the pressure at the bottom of the tube increases. And for your justification, you can say the wood displaces some oil, increasing the height, and that leads to greater pressure.